For question 4, a two-stage process is used to separate H2S from a gas containing 96% of H2 and 4% H2S by volume. The H2S is absorbed in a solvent, which is then regenerated by air in a stripping column. The Henry's law constant for the absorption of H2S in the solvent at 0 degrees Celsius is 22 atm per mole fraction. Calculate the molar flow rate of pure solvent and the volumetric flow rate of the gas at G4. Okay, G4 is over here, neglecting the evaporation of the solvent in both columns. So we want to find the molar flow rate of the pure solvent and the volumetric flow rate of the gas at G4. This is our final. Now, so let's put in all the information in from the data process streams here into the diagram. Okay, put everything in. Now we're just gonna flip it over 90 degrees. So at equilibrium condition, which is at G1, we can use the Raud's at ideal conditions. So the partial pressure of H2S is equal to the vapor, the mole fraction of the vapor, the mole fraction of H2S in vapor form multiplied by the total pressure of the inlet G1 here, which gives us the partial pressure of H2S to be 0.072. So why do we need that? Now, we are going to use the Henry's law, okay, to solve for X3, right, which is over here at the absorber. Okay, question says the Henry's law constant for the absorption of H2S in the solvent. Okay, so we're gonna solve for X3 over here, which is by taking the partial pressure of H2S divided by the Henry's constant of H2S. So it gives you 2.67 multiplied by 10 to the power negative 3 mole of H2S per mole. Okay, so we'll start by doing the overall H2 and H2S balance to look for N1 and N2, which is the number of moles in G2 and the number of moles in G4. Next, we're going to use N2 and air flow rate to calculate the volumetric flow rate at G4. Then, we will use H2S and solvent balances around the absorber over here to calculate for N3 and N4, which is located at L2. Okay, N3 is located at L2 and N4, which is located at L1. Finally, we will solve for the solvent flow rate. So first, we're going to solve the overall H2 balance. So we'll take 100, which is G1 here, multiplied by the mole fraction of H2 equals to, so H2 you have coming out over here is 0.999 of mole fraction of H2 multiplied by N1, in which you get N1 to be 96.1 mole per hour. And we can then do the overall H2S balance, which is 0.04 mole fraction of H2S in G1, and that equals to 0.001 mole fraction of H2S at N1, which is given here at G2, plus N2, which is located at G4. Now we already found N1 from the overall H2 balance, so that leaves us with N2, the number of moles of H2S coming out is from G4 is 3.9 mole per hour. Now the volumetric flow rate at the stripper outlet, which is at G4 here, is the summation of the 200 moles of air plus your N2, which is your H2S that we have found here. So sum this up, but we want it to be in terms of volumetric flow rate, right? So we will multiply this. We will use the value for the standard volume of 1 mole of gas at standard temperature pressure, and then since the condition here is at 40 degrees Celsius, so we have to convert it in terms of 40 degrees Celsius, which gives us 5,240 liters per hour. Okay. Next, we solve for N3 and N4 using H2S and solvent balances around the absorber. So we have H2S, which is 100, okay, multiplied by 0.04 plus 0.002 multiplied by N4. So N4 is over here, that comes in, so in H2S, the mole fraction of H2S is 0.02 multiplied by N4 equals to outlet, which is 0.01 multiplied by N1. Okay, at G2 here, you have your H2S, which is 0.001 multiplied by N1 plus N3 multiplied by X3, which we do not know. Okay. So, but we have already found X3 from here. Okay, X3 is 2.67 multiplied by 10 to the power negative 3. N3 is coming up from here, and we rearrange the equation, simplify it, and we get this equation out. Right? Now next, we will do the balance for the solvent. So the solvent we have over here at L1, which is 0.998 multiplied by N4, okay, equals to, at here, so the solvent is the mole fraction of the solvent is 1 minus X3, which is the mole fraction, X3 is the mole fraction of H2S in this L2 stream, multiplied by N3 over here, which is located at the stream L2. So simply solve the equations simultaneously, and we will get around 5,820 moles of solvent. So the values may differ slightly because of the number of decimals that were used, but it's okay. It will, as long as your method is correct, then it will be fine.